Hi guys, and welcome back. Today we're starting Module 6 Acid and Base Reactions Inquiry Question 2. And so what we're going to be looking at here is the role of our water in our solutions of acids and bases. So as we've talked about in our last video and in class, we've been looking at the Bronsted-Lowry theory. And it just builds on those limitations that the Arrhenius theory had and sort of, I suppose, fine-tuned the definition of what an acid was. So instead of it being just the transfer of hydrogen ions, the new definition is now an acid is a substance that donates one or more protons or hydrogen ions, and a base is a substance that accepts those protons or the hydrogen ions. And we have these other substances which we haven't heard of before called the amphiprotic substances, and they are substances that can act as an acid or as a base. So you can see here we have our water molecule, and our water molecule can either accept a proton and making that the hydronium ion, or it can donate that proton, in which case it becomes a hydroxide ion. And you can see in the examples below here where water is acting as a base in the first equation there, where we've got hydrochloric acid plus our water, and our hydrochloric acid is donating the hydrogen ion to the water. So the water is actually accepting that proton or that hydrogen ion, in which case it is acting there as a base because it's a proton acceptor. In the second example, however, we've got ammonia is accepting the proton from the water, in which case water is now acting as an acid there. So this is just our general equation that we look at with our Bronsted-Lowry acids and bases, and we can see that on each side we have a proton receiver and a proton source of the equation. So these are called our conjugate base or acid-base pairs. So you can have a look in this example we just looked at before. You can see that hydrochloric acid is our conjugate acid, and its matching partner on the other side is the conjugate base. So you can see the difference, HCl on one side, Cl- on the other. It's lost that hydrogen ion, or it's donated that hydrogen ion. And the same can be said with the water. The water is H2O, and you can see there that it has gained a hydrogen ion and making it that hydronium ion. So what we're going to look at in class tomorrow is the pH scale. So you've done a prac already looking at natural indicators and some of the colours that they change in a variety of different household substances. We're going to do a similar thing in class, and now what you're going to do is you are going to test the pH rather than just what colour change it makes. You're actually going to measure the pH of each of those solutions using a pH probe, a pH meter, and also some universal indicator. So that indicator is usually used to determine whether a substance is acidic or basic, and depending on its pH, it'll tell us the degree of acidity. So some of those ones that we might have looked at before, like phenolphthalein, it'll just be clear and pink. It's not actually determining and giving us an exact pH. So we're going to actually be looking at pH now. And we usually as chemists are needing that precision there, and that's when they came about with the quantitative measure called the pH scale. So what does pH stand for? It means power of hydrogen. So this came about due to the scale based on the concentration of the hydrogen ions in solution, or the hydronium ions in an aqueous solution there. So it again sort of reflects the importance of that Bronsted-Lowry definition as proton donors. So if there's an increase in the concentration of hydrogen, that'll be reflected in the pH scale. So here we have the pH scale on the left-hand side here. Now, if you actually look down there, you might be able to see a relationship between the pH, so 0, 1, 2, 3, the power to the base 10 that it goes to, and then also look at the concentration on the right-hand side. So if I have a pH of 1, it is 10 to the power of 0. Sorry, if I have a concentration of 1, it's 10 to the power of 0. Which anything to the power of 0 is 1, and that brings about a pH of our 0. If you have a look at pH 14, its power is 10 to the minus 14, so there's 14 zeros there, and you might be able to see that concentration that's happening. Our range generally goes from 0 to 14. We do have things that fall outside this measure, and there's sort of some special circumstances. We might talk about those a little bit later, but generally we have from 0 to 14. The lower the pH, the more acidic that solution is, the higher the pH, the more basic that substance is. Now this is a tricky part with sometimes people will say less than or equal to 7. Well, it's not. 7's our neutral substance. So if we are having acids, they are pHs less than 7, and bases are greater than our 7. So in class tomorrow, you're going to be looking at some of these pieces of equipment. You can see the dot point on the left-hand side. Conduct a practical investigation to measure the pH of a range of acids and bases. So really, to be able to answer this question, you're needing to look at, well, what is pH? What is the pH scale? What does that reflect? And also, how are we going to measure it? So we are going to do this tomorrow with our pH meters, our pH probes, and we're also going to use our universal indicator. You would expect that our pH probes or meters would be more accurate or more precise, which as chemists is what we're wanting. However, that is all dependent, of course, on them being calibrated. If they're not calibrated, then they may not be that accurate for us to use.